Hello. In this video, I'd like to outline the types of questions that you'll see this week on test number 3. As I had mentioned in class, the test number 3 is made up of only word problems, and there are 5 problems to complete, each with 2 parts. In question number 1, you'll be faced with a law of uninhibited growth problem, so this is an exponential growth question. In part 2, you'll be asked about exponential decay. Both of these are very similar in that both questions tend towards 0, either to the left or to the right of the function. Unlike that, however, the Newton's law of heating and cooling does not tend towards 0. There's an ambient air temperature that we must account for, so that makes this setup just slightly different for number 3. In number 4, we have a logistic model equation, and if you recall, those are the expressions that had some sort of exponential equation in the denominator of a fraction. And then lastly, the final question of the test will ask you to fit data, or fit an equation to a set of data. Now, for all 5 questions, the calculator will be permitted. So there's no break in between the parts of this test. It's all calculator permitted. You'll have it available the entire time. And each question is worth 20 points. Now, generally speaking, you'll have to do one of 2 things at the start of the problem. Either use the given formula to answer a question. If the formula is complete, you can actually use that formula to answer a question. Or if the formula is incomplete and we give you just pieces of information, then you'll likely have to identify the growth factor before you can answer the question. For the second component, or an additional part of the problem, we would again use the growth factor to answer additional questions about the scenario. So here's one example of what I mean by the 2 parts to each problem. We'll just quickly work through this, and then I'll respond to any questions that you have that are sent to me through email or through Schoology messaging. In this particular case, we've got a population that follows exponential law. The population doubles in size over 13 months. So this looks like an exponential growth, and it's probably going to be real similar to what we see in number 1. The current population is 10,000. What will the population be 5 years from now? Now, if I want to know what the population is 5 years from now, I need to know the growth factor. I need to know how fast it's growing. The fact that it doubles in 13 months is helpful, but that doesn't tell me how much it grows every year or every month individually. So we're going to have to calculate that the growth factor. In addition to finding the growth factor to answer this question, we will use it to answer this question as well. So let's get right into it. If we use the format that I'm more comfortable with, we would start the problem like this. Now recall that a population starts at some beginning value and then it increases towards infinity, but if we look leftward on this graph, it's tending towards 0. Doesn't mean anything for us in the word problem, but the graph tends towards 0. If we're dealing with a graph that doesn't tend towards 0, like the Newton's law problems, something like this, we have to account for that horizontal asymptote. In Newton's law, that's the ambient temperature, by incorporating this extra component. So be mindful of that when you do a problem like part 3. But in part 1, we don't need that. So let's go with what we've got. Now we're told that the population doubles in size over 13 months, and it's currently 10,000. So if we're currently sitting at 10,000 members of this population and it doubles, well, now we're looking at 20,000 members of the population. So the end result is 20,000. The initial value is 10,000. We don't know the rate at which it's growing per month, but we do know that it's growing, or it's doubling in size after 13 months. It changes from 10,000 to 20,000 in 13 months. After we divide both sides by 10,000, we're left with 2. And after we take the 13th root of both sides of the equation, we find that a is equal to the 13th root of 2. There's our growth factor. We're not particularly interested in reporting this answer, and we definitely don't need it as a decimal, so we're going to go straight on to the technically the first question of this problem. What's the population going to be 5 years from now? Well, let's keep in mind that this number 13 was a unit of time measured in months. So when we execute this new equation, we must also use months as our unit of measure. I know that it represents time, this x value represents time, but we must also have the same unit as well. So we better switch this to 60 so that we're talking about 60 months time, which is equivalent to 5 years. We have 10,000 members of this population times the 13th root of 2 raised to the 60th power, and now I'll reach for the calculator. So even though the calculator is permitted on this test, I would like to see your setup and not just a final answer. In fact, if final answers only are shared with me, then a significant deduction will be applied. I need to see your setup. I need to see what you're typing into the calculator in order to obtain your answer. So over here on the calculator, I'm going to enter what I've written on paper, 10,000 times the 13th root, 13th root of 2 raised to the 60th power. Again, the 60 represents our 5 years' time. And I'm okay with decimals at this point, so when I press Control Enter, I knew that the answer would come back as a decimal. In reality, though, a population can't really have a portion of a person or a portion of the population, so we'll go ahead and round this to whole numbers. The instructions on the test aren't going to be real specific about that. However, what I would like to see is an answer with 4 decimal places and then rounded appropriately, whatever you think would be appropriate for the particular problem. So let's go ahead and report that this is equal to 245,114 114.6171, or 72 if we had rounded to the 4th place. And since we're talking about people, then we should really say something like this: 245,115 people. I would like to see, again, all of this on paper when demonstrating your understanding of this particular problem. Now, if this answer seems pretty large to you, hopefully you're not too surprised by it. It certainly is a lot larger than the population began originally, but let's keep in mind that the population doubles almost every year, every 13 months. So in 60 months' time, in 5 years, the population doubles 4 or a little bit more than 4 times. So if we had 10,000 and doubled it, and then doubled it and doubled it 4 times, that's where this notion of 245,000 comes from. So this population is growing extremely fast. The problem goes on to ask, how long will it be before the population reaches 35,000? Well, this time we don't know how much time passes, and instead we're looking for that time, x, how long it takes to reach 35,000. Well, we know that we started with 10,000 and we're growing at a rate of the 13th root divided by 2, and now we can solve for x, the unknown in the exponential. So I'll divide both sides by 10,000. And I recognize that I'm dealing with an exponential expression at this point. Don't know how to solve for x in this particular form, so I'll switch it to a logarithm. The base of the logarithm requires the same base as the exponential. This time we're evaluating at 35,000 over 10,000. And that end result should be equal to x. So when I go to the calculator and apply the logarithm with the base of the 13th root of 2, evaluated at our goal of 35,000 divided by 10,000. We end up with a result of 23.4956. 23.4956. Now again, in this case, we're solving for x. X represents our time. And the time in this particular problem had a unit not of years, but instead months. So this would be fine as a final answer. If you think it would be more appropriate to round, now would be the time to do so. And you would say something like this. In the 23rd month after this population growth example began, we've reached now 35,000 members of the population. So I hope that clarifies a few things. I'm not going to go through all the different types of questions, but at least you see a better idea of calculating our growth factor, using that growth factor to answer a question, and then using it in another way to answer a slightly different problem. The exponential functions often require logarithms to solve, and I think that would be a fair question to ask on this test. If you have specific questions, as always, please let me know. I'll try to record a response and send them back to you. Otherwise, we'll catch up with you later. Thanks for watching.